We got to start by being formal, Dylan. Functions of several variables. All right. And Dylan, I'm gonna write with my pinky up. All right. So our notation for functions of several variables. We're going to say something like z equals f of x, y. Or, that's for a two-variable function. W, if we can continue, x, y, z, etc. So we can make our function a function of as many variables as we want. We are already familiar with functions of more than one variable. We know that, for example, that work equals force times distance. So work depends on the force and the distance. It's a two-variable function. We usually manipulated things so that we could treat it as a single variable function. Or volume of a box. There we go. Volume equals length times width times height. So that's a function of three variables. And we say f is a function of x and y, or x, y, z, and the set of pairs x, y, or triples x, y, z, depending on how many variables, is the domain. And the range is just the set of possible values of f. So our domain, we have to, when we're talking about our domain, we have more than one thing to consider. And our functions, multivariable functions, combine just like single variable functions. So what we're saying here is that if we add two functions, f plus or minus g of x, y, I'm just going to write it in notation with two variables. We just add the two functions, f of x, y plus or minus g of x, y. We can multiply the two, f times g, and that's just f of x, y times g of x, y. And we can divide the two. It's going to be f divided by g. With the caveat here, like we always have when we divide, the denominator is not 0. And we can compose functions, the composition, now the interesting thing about a composition is g would be a single variable function because our output from h of x, y is a single quantity. So g would be, we can compose a single variable function of a multivariable function. All right, for what we're talking about in 13.1, we want to introduce multivariable functions, but what we're most interested in this section is how we visualize the graph of a multivariable function, and how we represent different ways we can represent graphs of multivariable functions. Because what we're thinking of here for z equals f of x, y, we plug in an x and a y and we get a z value, we get a point up in space. Well, the set of the range of that function, the set of those points is going to be a surface. So we want to talk about how we visualize these surfaces, and the surfaces get much more interesting than the surfaces we've talked about so far. All right, so I want to start with a function, and we talk about it for a second, and then we're going to kind of go a little further. So just as an introduction. So for example, let's say we want to sketch, and there will be a lot of sketching in this chapter.
Yes, favorite part. I'm going to be an art major. So make more money.
Is that a piecewise function or?
Yes. So f of xy is x times y for x greater than or equal to 0, y greater than or equal to 0, and a 0 everywhere else. So before we start sketching, what is the domain? We have x greater than 0, greater than or equal to 0, y greater than or equal to 0. So in terms of our coordinate system, where is that? X, it's a first octant, right?
Yeah, first
Our domain is a first octant. X and y are both positive, and we're excluding the axes. And the range so what about the range there? 0 to infinity. Z has to be greater than or equal to 0. Because these are both always going to be positive. All right, so to visualize this thing, we're going to, for this particular one, there are a lot of different ways that we can visualize. Let's pick a particular value of z. And actually, to sketch this, I'm going to make my x-axis go out at more of this angle.
Don't do it.
Because it's easier to sketch that way.
I hate drawing.
All right, so for this one, we're going to pick a z value. Pick z equals 25. So just because. Well, if z is 25, then x equals 25 over y, and y equals 25 over x. What are those things? What are the graphs? Those are hyperbolas. xy equals 25. xy equals 25, that's a hyperbola. Just like xy equals 1. So you get hyperbolas like this. So here is z equals 25. And we're going to get some kind of something that's going to connect this down to the x-axis. And then the surface is going to, it's 0 on the axes, so it's going to go from this point down to the x-axis and down to the y-axis, and it's going to go from this point down to the x-axis down to the y-axis.
It's a teepee.
So it's kind of like,
Is that a line or a
that would be a line. So it's kind of like,
Integral.
it's kind of like if you staked two sides of a tarp to the ground and you picked up one corner. For example, like that.
Like
Wait,
a teepee.
so it's like a teepee shape.
Sort of like a teepee.
not like it's pretty straight. Is it more curved than that though?
Not more curved,
But it has a line.
but if you found for a particular z value, if you found where z was constant, you would trace out on that. You would trace out a hyperbola. Where z is constant, you would trace out a hyperbola. So if you're walking on a level piece of this surface around the edge, you would have a hyperbola. And I have a picture, another picture here. Where's my pen? There's a graph,
Teepee.
sort of a teepee shape, but you can see the curve. If I go this way, you can see the curve.
It's like kind of.
Yeah, it's kind of curved, right?
So it's
So it's not.
It's more like
Whoa, it's like a.
like you were to take a piece of like fabric and lift it. How
Yeah.
it kind of
Yes.
bend like that.
Yeah,
Okay,
yeah,
so
yeah.
that was very stiff. Looking.
Yeah, that was stiff. It's because it's relatively small, also.
But if it was big, it would be
Right.
more curved.
And this would continue going up
So
for
what
any.
makes that like line to go to Z? Like the line in the middle that we just drew. What makes that? And then like how does
What part of the function makes that?
R confused stay one?
So you'd think about the projection onto the xz plane or the yz plane.
It's just a line.
Yeah.
Where are the hyperbolas? Like
So if we walked along this surface if z at a constant value of z, we would walk along in a curve kind of like that. So if that's a hillside and we're staying at the same elevation, we would walk along a hyperbola.
Oh, so if you like cut that.
Right.
And it's hyperbolic with what? Like, isn't a hyperbola usually the two sides?
It's only one part.
This because we limited
Positive.
x and y to be positive,
Oh.
we don't have the other side.
So if you were to
If
like
we-
cross-sectional slice.
Right, if you took a cross-sectional slice for a constant value of z, kind of a slice like this, you would slice out a hyperbola. All right.
What do we stick like this? Oh man, hey, real Fortnite.
Now I have some questions for you. Let's say we have z equals f of xy. I want to know how would the graph of this function that I write up here compare to this one. G of xy is f of xy minus 3. Yeah, that's going to shift it 3 units down. So whatever the graph looks like, G would be shifted down 3 units from the graph of f. And by down, I mean in the negative z direction. How about g of xy equals negative f of xy? XY plane, there we go. It's reflected in the xy plane.
Hey, Brett. What's a 2D axis?
So I think there's a homework problem that asks you about the map of the ocean floor, and it has to do with the reflection, because if you reflect the function, then you get not a depression, but you get like mountains versus valleys. How about g of xy is 1/2 f of xy. Yeah, it's going to compress. And we're going to compress it vertically.
Special triangles?
Oh, yeah.
Okay.
All right. So our intuition about how functions behave in general is the same as how multivariable functions are going to behave. Now, when we were talking about the function, this kind of tent side of a tent function here, and we were talking about the hyperbolas and the cross sections. Those cross sections are one way that we're going to use to visualize these graphs of multivariable functions. So we're going to talk about contour maps. Level curves, and contour lines. All right, in order to make a contour map, in order to get a level curve, we sketch curves f of xy equals a constant. And we draw those on a two-dimensional surface to get an idea of what the surface looks like. An example of a contour map where you're thinking about the level curves that are made of contour lines is a topographical map. So if you've ever gone backpacking, you get these topographical maps that have all the elevation lines. Those are constant elevation lines. So you look at this topographical map and you can get an idea of what the terrain looks like. If the lines are really close together, you know that the mountain is really steep. If the lines are really far apart, you know that it's relatively flat. The other thing, another example is a weather map. So on the weather map, they map out where the barometric pressure is constant. And you get these kind of lines, these loops of lines where the barometric pressure is constant. So you get an idea of what the barometric pressure in a certain areas looks like. Another example is if you sketch equipotential lines for an electric field or a magnetic field. So you're sketching lines where the field is constant. So you have an idea of how the field is varying. If the contour lines are far apart, means that f is changing slowly. So if our lines are far apart, the constant value of z means from one to the other, z hasn't changed that much. We haven't gone uphill or downhill that much. But if they're close together, it means it's changing rapidly. And usually we want to pick a value for the constant so that our lines are evenly spaced apart. So we have the constant equals 1, 2, 3, 4 to get an even spacing or consistent spacing. So on your topographic map, the legend will say how far apart in elevation the lines are. So if they're really close together, that means the elevation's changing really quickly. If they're really far apart, the elevation's changing slowly, but the map will tell you what the value is. the elevation between two lines is 50 feet or something like that. All right, so what I want to do is, let me make sure that I have this here. Yes. All right, so we're going to match. We want to match the, we want to match the surface with its contour map. So these are contour maps of the various surfaces. The lines represent constant z values. So we want to match these maps.
We know that D is associated with number 46.
All right, so Kira says D. I'm going to say 45 here, and I'm going to jump down to 46. Kira says D has to be 46.
First of all, you just look at the shape of the graph.
You look at the shape of the graph, you look at the shape of the surface, so you can kind of visualize this thing, some hills here, some hills here, and it's going to get that thing. 45 is C, because if you look down on this from the top, or if you think about cutting a slice out of this, you're going to get circles. So 45 has to be C. And I'm leaving some space here because I'm going to show you how we get the equations for these contour lines from the equations of the function. All right, how about 47? B. We have these parabolas, and we have this kind of parabolic shape here. So 47 would be B, and 48 has to be A. So this is kind of a, if you think of dropping a stone into a pond, that would be kind of the map of the ripples in the pond. But it's elliptical shaped, so that's a little strange. All right, let's look. Folks, listen up. Let's look at how we get the equation of the level curves from the function. So 45, we said, was C. So 45 is f of xy is e to the 1 minus x squared minus y squared. To get the contour lines, to get the level curves, we're going to set that equal to a constant. E to the 1 minus x squared minus y squared equals a constant. And I want to get an equation in x and y. So what do I do here? Take the natural log of both sides. So I get 1 minus x squared minus y squared equals natural log of c, which is just a constant. So I'm going to C1. I'm going to add the x squared and y squared and subtract the C1. X squared plus y squared equals 1 minus C1. This is a constant.
What?
That's a circle.
Oh my goodness. What?
So that would be how I would find the level curves of this function. The level curves are circles.
Okay.
Number 46, we said was D. These level curves are hyperbolas. So 46 is f of xy equals e to the 1 minus x squared plus y squared. Set that equal to a constant. E to the 1 minus x squared plus y squared equals a constant. Take the natural log. 1 minus x squared plus y squared equals some other constant. Natural log of this constant. And then I could write y squared minus x squared equals c1 minus 1, which is another constant. These are hyperbolas. For b, we said 47 was b. Natural log, absolute value of y minus x squared. Set that equal to a constant. We want to get an equation in x and y. So what do? Exponentiate or rewrite in exponential form. So we get y minus x squared is plus or minus, I'm taking away this absolute value, e to the c, which is a constant. And then I can rewrite that as y equals x squared plus or minus e to the c. Parabolas. And finally for a, f of 48, f of xy equals a cosine of x squared plus 2y squared over 4. So we set that equal to a constant. Equal to a constant. So x squared plus y squared over 4 plus 2y squared over 4 is the inverse cosine of our constant, which is another constant. And these are ellipses. So that would be the procedure. If your problem says sketch the level curves for this particular function, this is the procedure you use. And you can make a nice contour map with your level curves. All right, let me see what's on. Oh, unless I have a 3D version of these surfaces. All right. So there's that one, that first one. So we get this, if we look at it from the top. So that's our. There's that, our hyperbolic paraboloid. That's a Pringles shape. There's your hyperbolas. There's that. That's the one with the parabolas. So looking at this graph, what are you guessing is happening here? What's that? The function, well, we don't really have asymptotes for multivariable functions. Our function's undefined. Well, this is the natural log of something. Where's the natural log undefined? Where the argument is 0. So where y equals x squared. That's that parabola. So that function is undefined along that parabola. So, listen up. Multivariable functions are not only undefined at points. They can be undefined along an entire curve. And the next one, there's that cosine one. No, this just it would just keep going. Yeah. All right. Let me see what I have on the next. I want to do. All right, let's sketch the level curves of f of xy equals natural log of x minus y And for this problem, we're going to say c equals 0, plus or minus 1/2, plus or minus 1, dot, dot, dot. What are our level curves here? Lines. X minus y equals e to the c. These are lines. And our slope? Y equals e to the c minus x. Negative 1.
It would be x minus e to the c.
Oh, x minus e to the c. Thank you. Slopes of positive 1. And where are these, where we're going to be able to have these lines? So we don't end up with so we don't end up with an undefined argument
X
there.
cannot equal y.
X can't equal y, so we can't have them along the line y equals x.
I think that's it.
We can't have a negative argument, right?
Crap.
Y can't be greater than x.
Y can't be greater than x, so y is less than x. So we end up with these lines. So if we sketch our level curves, we're going to have level curves something like this. And if we sketch these for these values, they would be close together here and get further apart here. So what would that surface look like? Well, then we have a natural log here, so the z value is going to be logarithmic. Right, so we're going to have like a what did you call it, Sean? Like an exponential ramp. That's a pretty good description. So let's take a look. There it is. So there's your natural log function, or your lines.
So it's like a natural log function that's been like extruded
Right,
out.
right.
Yeah.
And it's steep here because our natural log function has an asymptote at 0. So there's our surface.
Really nice. No, you couldn't fill it.
All right, questions? Oops, that's not what I wanted. Hit the wrong thing.
Cool.
All right, these next ones. For these next ones, let's describe the surface.
Flat.
Yeah, it's like in the Grand Canyon.
Like a bird race game.
Connor cannot talk.
It's like a valley, and then you talk.
Right, it's like a valley. So valley on one side and hills on the other side.
And that's like the next one is like an
Wait, so what did we call this surface? We talked about these surfaces before. There. Yeah, it's a hyperbolic paraboloid.
Oh yeah. You just cut me off short.
Saddle shape was the other way that we thought of it. It's Pringles. It goes down here and up there.
Is there any way to tell whether it's going up or down?
Not without more information. So let's see. I think I have that one. Do I have that one mapped out? No.
So, Mr. Beaver, based
Yes.
off of that, we can like assume that everything's just going down, or we can assume everything's just going up. We don't know for sure.
You know, if everything. So that's a good question. What would happen if this were downhill on all the sides? What would happen here at this point, or this point?
It'd be
Wouldn't it be level there?
Yeah, so it wouldn't be able to.
So you'd have a line, a contour line along the top there.
So that has to be the bottom part.
That has to be the bottom of one part, the bottom of this part, but the top of this part. Because otherwise it would be level. If it were the top of both parts, there'd be a part there where it's a level, and you'd have a level curve along that level point. All right, how about this one?
It's like the top part of an ellipsoid.
What is it? Oval-shaped bullet? Yeah, okay. Bullet? I thought of a bowl.
There you go.
Do we know it's going in? Is it going in or out? Can we tell?
Because then that it's
And we,
curved no matter what.
we can't tell unless we know how our constants are changing, whether this is the high point or that's the low point. So it could be an oval dome.
So would this be like half of an ellipsoid, like you cut off?
Yeah, this would be like an upper part of it, an ellipsoid, or the lower part of an ellipsoid.
Well, it would be both parts, just whether you're looking at it from underneath or above.
Right.
Stretched out. Okay.
All right. How about Kyle? How about not a bullet? How about a cannonball? There we go. An oval cannonball. Yeah, because you can just shoot it out of an oval-shaped barrel, and it doesn't have to spin. It's just a cannonball that flies through the air. All right. So our homework. Our homework today is all has to do with visualizing these surfaces. Next time we'll talk about limits and continuity, and then we'll start getting into doing some calculus. Some interesting things happen with limits and continuity.
Fantastic, interesting things.
How about just an oval-shaped projectile? We'll leave it at that.
Ocular projection making my life hard.
Hi, Calc. There's a 64 and a 69. I know about how much we beat with that. Never mind.
Sorry, those got messy. Someone was talking to me as I was writing them. I got distracted. All right, for number 60, for number 64, use not the function that they give you. Use f of xy equals x squared plus y squared. They give you a different function, but I want you to use that function. For 64e, graph z equals f of 1 comma y and z equals f of x comma 1 on the surface.